In this video, we're going to talk about applications of the fact that we've shown that analytic functions and holomorphic functions are the same thing. The first thing we're going to do is look at local description of analytic functions, and after that we're going to get into how the holomorphic closure properties, such as the product of two holomorphic functions is holomorphic, translates to formulas for analytic functions, namely formulas for power series. We'll also get into some convergence theorems for analytic functions that use the methods that we use to prove that analytic functions and holomorphic functions are the same thing. As a bonus, we'll also state and prove Newton's binomial theorem for general power functions at the end. Here are some of the deep thoughts for this video series. Now that we know that analytic functions and holomorphic functions are the same, we have to use this fact. So one of the main things is that it's easy to prove that a function is holomorphic because you're just checking complex differentiability and continuity of the derivative. It's also easy then to show that holomorphic functions have a bunch of closure properties, like the product of two holomorphic functions is holomorphic, and compositions are holomorphic, and so on. But what's not so easy to understand are the local properties of holomorphic functions, and analytic functions and power series properties are much better at establishing local properties. So here we can give a local description of analytic functions, which would be hard to do straight from complex differentiability. Let's see, so if we have an analytic function f, analytic at z0, and I'm always going to mean that to say that f is analytic on a neighborhood of z0, or it has a power series representation that converges on a disk centered at z0. We also want to assume that f is not identically 0. And then if f is not identically 0, then there's going to exist a natural number such that f equals z minus z0 to the n times an analytic function g, where g is also just analytic at z0, and g of z0 is non-zero. And one thing this tells us is that f is actually non-vanishing on a punctured disk centered at z0, because this function g will be non-zero for z close to z0. And so then f will be non-zero for z close to z0, but not equal to z0. Of course, we do allow for this capital N to be 0, which would mean that f just doesn't vanish at z0. But this is a local description of f in terms of its 0. So we call capital N the order of the 0 at z0, if there is one. And so the proof of this fact here, of this local description, is, well, we take the first non-vanishing coefficient of f's power series. Let's say it's a capital N. So then f's power series will start at capital N. So we can write it out this way, but then we can factor out z minus z0 to the capital N and re-index things so that we have a power series starting at 0, and this is what we'll call g. And then we're done. This power series here will converge on the same disk that f converged on, and g has the value an at 0, which is non-zero. So that does it. So most functions you run into in the wild will just have simple zeros, and you kind of have to work to come up with functions that have higher order zeros. But here's just a good example. Sine of z has simple zeros at all of its zeros. So its zeros are at points of the form pi times an integer. And how do we know that they're simple? Well, we can compute sine's power series at any of these points. So let's maybe write sine as f just so it's easier. And so f around one of these zeros will look like f of, let's say, pi n plus f prime pi n z minus pi n plus higher order terms. And just because the derivative at pi n is going to be non-zero, that's what this computation is. The derivative of sine is cosine, and if you evaluate that at pi n, you get minus 1 to the n. So sine has the basic power series expansion. It starts with coefficient minus 1 to the n, as z minus pi n. There's a typo there, no z. Plus higher order terms here. And this shows sine as simple zeros at all of its zeros. Well, sine plus tangent does have some zeros of higher order. The reason is we have that it factors into sine on top and cosine plus 1. And again, sine of z had simple zeros at pi times the integers, while cosine plus 1 has zeros at pi plus 2 pi z. But this has zeros of order 2 on this set, because, let's see, if we take the first derivative, we get minus sine, which vanishes on multiples of pi. So it has to have a zero of at least order 2, and then you take another derivative and get minus cosine, and then on these points it'll be minus cosine, I guess, will be 1. So we get a double zero here and a single zero here. So we have zeros of order 3 on these points. Of course, we still have the simple zeros at the other zeros of sine. Okay, so by our local description, we already know that analytic functions that are not identically zero locally will just look like a power of z minus z naught to the n times something non-vanishing. And as we said, this means the zeros will be isolated. So around every zero, you can find a disk where there's only one zero, possibly with some order. We can say something a little bit stronger using the connectedness of the domain, that zeros cannot accumulate in a domain. So let U be a domain, and let F be analytic on that domain and not identically zero. Then the zeros of F cannot accumulate in U, so they do not have a limit point in U, meaning I cannot find a sequence of zeros inside of U that converge to a point in U. They have to kind of go to infinity or go to the boundary of the domain. So how is this proven? Well, first, we just want to point out that if we had a sequence of zeros inside the domain that converged to a point in the domain, then we would have non-isolated zeros. And so by our local description, F would have to be identically zero on a neighborhood of such a point in the domain. So that's the local aspect. Then the more global aspect is the connectedness. So let's consider the set of all points where there exists R such that F is non-vanishing for W's within R of Z but are not equal to Z. And so these are actually just the points with the property that on the neighborhood of that point, F is not identically zero. Okay, but the set is evidently open because if a point has this property, then for nearby points, it's non-vanishing, so there's no issue. But by the local description, this set has to be closed too, because if a point is not in this set, then it means you cannot find such a radius, so there have to be a sequence of zeros tending to a point, and that forces f to be identically 0 on a neighborhood of that point. Okay, and so we're assuming f is not identically 0, which means the set A is not empty, and so A has to be all of U by connectedness. And remember, domains are by definition open sets that are also connected. Okay, and then we get out of this that zeros cannot accumulate, because if they did accumulate somewhere, then there would be some point with the property that on a neighborhood of that point, f was identically 0. But the set A is all of U, so there are no neighborhoods on which f is identically 0. It is worth pointing out that we can get infinitely many zeros in a domain, but they have to kind of tend to the boundary or tend to infinity. So certainly sine of z in the complex plane has infinitely many zeros, but they don't accumulate, they head off to infinity. We can modify this to get infinitely many zeros on a set like the disk. Here I've just plugged in a fractional linear transformation that maps the disk to the right half plane. So we'll get infinitely many zeros on the disk for this function, because I can hit all of the zeros of sine that happen to be on the positive reals. Okay, so we can have infinitely many zeros in a domain, but if we have a compact set inside a domain and f analytic on that compact set, well, f can only have finitely many zeros on the compact set. That's just by compactness, because if it had infinitely many zeros on the compact set, then a subsequence would converge, and they would converge inside the domain, so that's not allowed. So analytic functions will have finitely many zeros on compact subsets of their domain. Okay, out of the fact that the zeros cannot accumulate, we can get something called the identity theorem. That just says that if I have two analytic functions on a domain U, and if they agree on a set with a limit point, then they have to be identically 0. This is just the fact that f minus g is analytic, and the assumptions say that f minus g has a sequence of zeros that accumulate in U. So by the previous theorem, f minus g has to be identically 0. So this is useful in all kinds of places. Here's a good example. We know that cosine squared of x plus sine squared of x is equal to 1 on the real numbers. And the real numbers certainly have a limit point. So this identity automatically extends to the analytic extensions of cosine and sine. So you get that cosine squared plus sine squared equals 1 on the complex plane without having to check any algebraic identities.